disable those weak key types. Get rid of DES, get rid of export grade, RC4, and if possible, stick to the AES ones, just because they do have that additional password complex, or the the computational complexity for deriving the key from the user's password. In addition, there's a different mechanism for deriving keys from the user's password that makes it so that even if you do break that encryption key, if through some grand advance through cryptography you are able to break that 256-bit key, you still can't forge a timestamp because it itself is a derived key. So disabling E-types, it's always configurable in MIT and similar distributions. Windows Server 2008 and R2 and Windows 7 introduced a new policy that allows you to configure E-types. And also these are just increasingly disabled by default. In the latest versions of Windows and the latest distributions of MIT, you don't have to take any, MIT Kerb 1.8, you don't have to take any additional steps. So if we get rid of those bad E-types, we still have the possibility of password grinding attacks. If somebody sets a password of 12345 or Gandalf, you're still going to be able to see that timestamp. No matter how complex it is, you're going to be able to get an efficient recovery of that password and be able to spoof that user. The response people say is use smart cards, use the public key Kerberos authentication mechanisms, and Brad will talk a little bit more about his research in that area.
All right, so smart cards are the gold standard today for enterprise authentication. If you're in a highly secured environment, you probably use a smart card to log into your Windows workstation. And under the covers, that is all still implemented in terms of Kerberos. There's an extension to Kerberos called PKINIT, which allows for public key cryptography, usually X509 based PKI, and usually certificates stored on a smart card, to be used to replace this initial authentication step that Scott has just been talking about. So instead of using DES and AES encryption, we're going to use public key encryption. The client is going to send a pre-authenticator that includes a certificate and a signature made with the private key associated with that certificate. And the KDC is going to respond and send the ticket granting ticket encrypted with the client's key and signed with the KDC's key and providing the KDC certificate. Relatively simple, only the first leg of the protocol changes. So one of the key things that you always have in Kerberos is mutual authentication. It's not just that the KDC wants to authenticate the client, it's that the client also gets to authenticate the KDC, because the KDC is then going to be the authority for every other service that the client talks to. This is relatively simple and implicit in a symmetric key situation, because you know that the only other person that has your key is your KDC. So you have, as long as you can decrypt the message, it came from the right person. In a public key situation, things get more complicated. PKI, we have chain building, we have roots of trust, we have policies, we have subject identifiers, extensions, things like that. And as we've seen in the last couple of years with HTTPS and SSL, this can be rather tricky. There's a lot of pitfalls, there's a lot of things that can go wrong. So we want to look a little more deeply into what are the validation policies for these certificates involved in public key Kerberos. So first thing that's of interest is who are the trust roots. And luckily for all of us, the usual suspects from the web are not involved. That big list of 200 CAs of varying trustworthiness or not that ships with your browser and your operating system and Java and everything else, those are not in the picture here, and we're all very glad of that. All the certificates for public key Kerberos have to be issued by a specific set of designated trusted CAs. This is usually in your Kerb5 config file for the open source clients. On Active Directory, it's stored in the directory in LDAP, in the NT-auth store, and it's also stored in the registry. Now, when you're authenticating as a client with a smart card, the way that the KDC validates that smart card certificate is it has to be issued by that authority. It has to have a subject name that matches your Kerberos principal or is mappable to a Kerberos principal. And it has to have a smart card authentication enhanced key usage flag to distinguish it from just any other soft certificate that's being used. That's relatively straightforward and implemented in the same way by almost every implementation. Where things get a little trickier is how the client authenticates the KDC. And there's some big differences in the implementations here. You still have to have that certificate for the KDC be issued by that specially designated authority. And the open source clients look for a special key purpose ID and enhanced key usage that says this is a KDC. This certificate is not anything else. It is a KDC. And you have to hope that the certificate authorities are very careful about who they issue those kinds of certificates to. Now Windows was actually, the public key Kerberos implementation was done before the specification was finalized and before the CKU is set up. So if you look at the certificates issued to Windows domain controllers, they typically don't have that EKU. So that raises the question, then how are Windows clients verifying this? And for a long time, there was no documentation, there was no indication of what that algorithm was. But a couple years ago, with Vista SP1 and Server 2008 being released, there was a new group policy that appeared called Require Strict KDC Validation. And this is obviously pretty interesting. You would hope it was always strict. But if you look at the text here, it starts to just recapitulate the verification algorithm specified in the RFC. I won't bore you with that. But the last paragraph is especially interesting, caught my eye. If you disable or do not configure this policy setting, the Kerberos client will require only that the KDC certificate contain the server authentication purpose object identifier and the EKU extensions. That's it. Server auth EKU, and it can be a KDC. So are there other certificates issued by the enterprise authority that have this EKU? One of them is the web server template. If you're in a large enterprise, how many web servers do you have and how well are they secured? If you've been following advice of people like me who say you need SSL even on your intranet, you probably have a lot of these certificates floating around. Enterprise web applications are kind of notorious for their insecurity. They might not be patched, they might be running a mix of Linux and Unix and other operating systems. You have a lot of attack surface that allows someone on your network to potentially gain access to one of these certificates. And even if you're using network access control or something like that, you're guaranteed to have at least one system on your network that has one of these certificates, your remediation server. But unfortunately, it gets worse. Because when you install Active Directory certificate services, one of the templates that's enabled by default is the computer template. And this template also has a server auth EKU. And as you can see in the screenshot, every single computer that's joined to the domain has permission to enroll for this certificate by default. So what this means is potentially any computer in the enterprise has access to a credential which might allow it to impersonate the KDC to any other client in the enterprise. And we did some testing and verified that yes, in fact, that's the case. In the default configuration, all Windows clients up to and including Windows 7 and all of the open source clients when configured to interoperate with a Windows domain controller will accept PKINIT AS reply signed by a certificate issued to a web server or just using the computer template. You might wonder, well, why don't we just match the name? You know, I'm not expecting www.domain.com to be my domain controller. And it turns out you can't do this. This is our SSL, main part of our validation algorithm for SSL certificates. We can't do this for KDCs. First of all, it's not in the specification, so a lot of the certificates don't have a standard subject name field like that. And secondly, a lot of clients don't know who their DCs are when they boot up. They don't know their KDC. They have to discover it dynamically. They might have moved to a different part of the network. The administration configuration might have changed. So Windows clients are going to wake up. They're going to ask DNS SRV records. They're going to ask NetBIOS broadcasts. They're going to do a connectionless LDAP that's unauthenticated. A bunch of insecure protocols to try and get a name that they can then bootstrap Kerberos with. So there's no point in trying to match a name that you got from an insecure network protocol with the name you got in your certificate. So they don't even try. This has some interesting effects in the attack we're about to demonstrate, because if you don't do that match, you can't use DNSSEC to save you from this attack because the client isn't doing any name verification anyway. As long as you can ARP, spoof, or be an active man in the middle, you can supply whatever certificate you want, even if it doesn't match the name. And Kerberos traffic is also typically exempt from IPsec policy, so you can't rely on IPsec to protect you. So what does our practical elevation of privilege path look like? So here's our typical kinit, which is the command line used in our open source implementations on, say, a Linux system to do Kerberos and then go get a file from a file server. If we replace this and put in our imposter KDC, we can also replace our file server because we're authenticating who the file server is, and we can poison the protocol and allow for the spoofed file server location to be trusted by our victim. We can send them a Trojan or a piece of malware and take over their session. And it's actually relatively simple to accomplish. Turns out that at Windows, this is much more difficult, and the basic naive attack we just showed there fails. And this is because the victim isn't just authenticating to the KDC, the victim has to authenticate to their workstation. So they make their initial request, and then they ask for a ticket to log on to their workstation, and they send that ticket locally inside the machine where it can't be influenced by the network attacker to complete their authentication. So when we replace our KDC with the imposter with the web server certificate, we can still capture the initial part of the protocol, but when we try and do the last ticket, we don't know this binary secret for the workstation. That's still a secret that's only shared between the workstation and the real KDC. They never use public key Kerberos, so we can't create a real ticket that lets the user log in. And we're going to get a message saying something like, the trust relationship with the domain failed. But there are ways around that problem. Domain join is one situation where you don't have a machine account yet. We're bootstrapping trust, we're creating the machine account, we're creating the machine account password at domain join time, and it's all based off of the user's credentials. So if we can intercept a man in the middle of domain join being done with a smart card, we can use that to capture and man in the middle all the traffic, discover the machine account's password, take control of it, and then when the user logs in again with permission, we can just forward that traffic, join it to the real domain, and we have a machine which we know the system password for as long as it's valid, and there's no forensic trace of us on that machine. But domain join is an unusual situation, right? You don't typically see that happening on a network if you're an attacker. Many machines are joined offline or pre-joined. We want to be able to attack regular everyday traffic. Well, let's assume we also have control of a conspiring user. If we have full control of a workstation, it's not too much of a stretch to assume we also have control of a user account with real credentials in the domain. Maybe this is a conspirator, maybe this is just someone that we've owned. There's this interesting feature of Windows Kerberos called user principal name canonicalization. This is used so that administrators can move your account around within a large directory between realms and to different parts of the organization, and you don't have to know that that's happening. You can always use the same email address to log in. And we have the RFC draft text up here for you, but the basic gist of it is that the subject on the certificate on your smart card is not definitive for what your Kerberos account and your principal is. It's only a hint. It's a pointer, and the KDC is authoritative for what your actual account is once you start getting these tickets. So if this is just a pointer, we control the KDC and we have a conspiring user. What if we make your logon point to and look at the conspiring user's account instead? So here's the attack scenario we've built here. We have our victim who's trying to log in, and we see they make their initial request and they say, hey, I'm victim and I would like to log in. I would like to get an authenticator and a TGT. And our imposter KDC says, sure, here's your TGT. By the way, your actual principal name is patient 0, which is our conspiring or pre-controlled account. Victim says, okay, you canonicalize me, that's fine. Now give me a ticket to the workstation. The imposter KDC, since they have credentials for the real user patient 0 in the domain and they can talk to the real KDC, and since most users can log into any workstation in a domain, they go ask the KDC as patient 0 for a real ticket to the workstation. They get it. They're able to unwrap it, unwrap the session key, and have the real ticket to the server issued by the real KDC. They rewrap it with the key they've controlled and given to the victim, send it along. This is a referral TGS reply because the name is different than the name that the victim thought. This will be accepted and they can use it to log in. So now we have a situation where the victim has logged in with their smart card, but they came in as somebody else. So is this really an elevation of privilege? We assumed at the beginning we had control of patient 0, and now we have a login session as patient 0. So we haven't elevated privilege yet, but we're in a very good position to, because a user started at a trusted, healthy workstation, has no malware on it whatsoever. They put their smart card in, they typed in their PIN, and they got logged on as someone else. They have no reason to expect that that's going to happen. That's completely unusual behavior. And furthermore, that login interactive session now we control. We have control of that patient 0 account. We have control of the KDC. We can change their login environment. We can run commands on that desktop. We can push group policy. So we'll push a Trojan that pops up the screen as soon as they log in that says, installing updates, please do not turn off your computer. And we hang around for 10 minutes, and then we pop the screen that says, insert your smart card to unlock your workstation and type your PIN. User types in their PIN, it unlocks, says, please wait, we're rebooting. They reboot, they log in again, everything's fine. But what really happened was they forgot to hit Control-Alt-Delete. Pretty common. They're used to putting in their smart card and typing their PIN. They think it's a trusted system. But really that Trojan program just captured their PIN. In user mode, it's able to unlock the smart card module, make a TGS request to the real server, and now it has a credential it can renew for up to 7 days and access any service in the enterprise as that user. Smart